Hello, my dear student. Welcome to another edition of your mathematics lesson. Today, in continuation with your main topic, that is depreciation and learning how to find the derivative of some special functions. Today, we are going to take the fourth techniques, and this technique is called the implicit rule. So let's begin. After completing the very lesson today, my dear student will be able to find the derivative of implicit function. This is what I hope you'll be able to do after completing the lesson today. So as usual in your favorite segment of the lesson, that is Mercy's Fun. Today I'm happy to introduce the relationship between the golden ratio and the Lucas numbers, that is the Lucas sequence. We see this very relationship. In fact, it's one of the properties of this Lucas sequence, how it relates to the golden ratio. I will explain this concept after completing my lesson today, so don't go away. To begin the lesson, let us also consider some special functions. Number one function says xy minus y squared equals to 3x cubed. And the number two special functions says y equals to yx raised to 4 minus 5y cubed plus 9. And these are special functions, which I believe in all the lessons that we have under this main topic, depreciation, we never see these types of functions. So these types of functions, to find the derivative, also we need to learn another new technique. And that new technique is called the implicit rule. And it is this rule that we are going to learn in this very lesson. So let me go back to these very functions. Look at this function number one and number two. Why they are different from other functions that we have seen before. In each of this, you see that y is not made subject of the formula completely, but in the rest of the functions that we have seen before, y is completely made subject of the formula. That is, you have y by the left-hand side, then by the right-hand side, you have only terms in x. But in this case, you can see terms in x and y all over. If you look at number one, you can even see here, this is a term in x and y. This is y only. This is x only. So in this case, number one, y is never made the subject of the formula. While in number two also, even this y that you can see here by the left, but there is another y by the right, which means y is never made subject of the formula. This is the difference between this type of functions and the other function that you have seen. And it is this type of functions that if we ask to find a derivative, that you now think of this implicit rule. So this function, we have to employ a different method of finding the derivatives. So the relationship between x and y in these functions above, that relationship is an implicit relationship, which means other functions that we have seen before, the relationship between x and y would now be explicit. But here it is implicit. So it is from this relationship between x and y that is implicit. We now have the name of this rule as implicit rule. So derivative of this type of functions, like I have said, require another extra special techniques, which we are going to learn shortly in this very lesson. So the rule for this very function, if you are to find the derivative of this type of functions, what it says, what you do first is to find the derivative of both sides of the equation with respect to x. So you have to find the derivative of each of the two sides of that equation with respect to x. And when you do that, number two simple is to solve the resulted equation for dy dx. That is, you have to make a dy dx subject, which we shall see these two steps when we come to example just now. So let us just move and take examples so that we can now make use of these two steps, these two guidelines to find the derivative of these types of functions. So example number one, it says find dy by dx, that is the derivative of the function with y with respect to x. If you have this function x squared plus y squared equals to 36. This is an implicit function because you can see here y is never made subject of the formula. Solution to this very problem. What we do first is to write down the given function, that is x squared plus y squared equals to 36. So next, You now find the derivative term by term because the first rule says you now find the derivative of both sides of the equation. So I'm starting with the derivative of x squared. Derivative of x squared, that is the very first term. Then the derivative of y squared. So I have d by dx of y squared. Then d by dx of the right hand side, which is a constant number 36. So I continue. So I'll now find the derivative of this very x squared. And the derivative of x squared will be, if done correctly, 2x. So derivative of y squared is what I'm going to do now. So just to hold on and wait and learn, pay attention here so that you learn something new. I'm finding derivative with respect to x, but this is not x, it is y. If I go back to this very one, I'm finding derivative with respect to x of this x squared. So it is a term in x. But here it is not a term in x, it is rather a term in y. But I'm finding derivative with respect to x. So what you just do, take it as it were x. But when you do when you find a derivative, that is, you have 2y. What you now have as difference is now attached, or you now multiply it by dy by dx. When you now find the derivative with respect to x of a term in y, what you now do, you now attached, or you now multiply the derivative by this dy by dx. This is something new. This is something new. So I'll continue. So I now find derivative of the right hand side, and this is nothing but a constant number 36, and we learned that derivative of constant number is 0. So there I'm going to have 0 instead. So this is done, that is step 1 is complete. That is, I have now obtained a derivative of both sides of the equation. So I move to step number 2, and step number 2 says solve for dy by dx. That is, I'm going to make a dy by dx subject of the formula. So to do that, I'll have to first take this 2x to the right hand side. There gives me 2y dy by dx equals to minus 2x. Then to find dy by dx alone, I have to divide both sides by this to 2y. So dividing both sides by 2y, you now have dy by dx by the left hand side, and the right hand side you now have minus 2x divided by 2y. There, this 2 and this 2 cancel each other. So you now have minus x all over y. This is the dy by dx of this very function. So let me just take one more example. This implicit rule. Example number 2, it says you have to find the dy by dx if you have the function x cubed plus y cubed equals to 5xy. Solution to this very problem, copying out the given function, that is x cubed plus y cubed equals to 5x squared. Looking at this function also, as y is not met subject of the formula completely, I will know that it is this implicit rule that I'm going to apply. So step number 1 says you now find a derivative of both sides of the equation. So let me start with that. So I'll now find derivative of x cubed, that is d by dx of x cubed plus the d by dx of y cubed, but then equals to d by dx of the right hand side, which is 5xy. So d by dx of 5xy. So what I'm going to do is to find the derivative of each of those terms. So derivative of x cubed, that will be 3x squared. And the derivative of y cubed, like I have said, I will repeat also. If you are finding derivative with respect to x, but the term is not in x, it is in y, then you now just find the derivative, then attached or multiplied by dy by dx. So derivative of y cubed is now going to be 3y squared, then times the dy by dx. Then I'll come to the right hand side. Here there will be a problem, but don't worry, we have learned the techniques. This is 5xy, that is 5 times x times y. So in this case, one of the techniques that we have learned before, one of the very first technique, that is the product rule. So to find the derivative of 5xy, you have to apply product rule here. Product rule, remember, is a function that can be expressed as a product of two other functions. So here I can see it as a product of two other functions. If I take 5x as one function, y as another function, so it's product of two other functions. Let me just to do this using the product rule. Then I'll come back and write the derivative. So let me just draw a line so that I can now find the derivative of 5xy here using my product rule, which I learned already. So derivative of this 5xy, first I will now later u to be 5x. This 5x is now your u. Then the other part of the function will now be y, which will be your v. So what I'm going to do next is to find the du dx and find the dv dx. This is what I'm going to have in the formula for product rule. So du dx, that is derivative of this u with respect to x, it will be 5 if you do it correctly. And the derivative v with respect to x, this is y, just like 1y raised to the power of 1. So the power 1 reduces, so it now become power 0. And that 1 power 1 will now multiply the 1 here. And remember, when we are finding derivative with respect to x of y, what we now do after the derivative, we now attached dy by dx. So there, dv dx, dv dx, it will be nothing but dy dx. I have 1 here, please. We don't usually write it because derivative of this y is nothing but 1. So 1 times dy dx. So dv dx is now dy by dx. So I'm now going to substitute in my product rule. And that product rule, remember, says, remember the product rule says v du dx plus u dv dx. This is the product rule, the very first technique that we have learned. So I'll now substitute my v, which is the function y, which is y, and the du dx, which is this 5, then substitute my u, which is 5x, and the dv dx, which is dy dx. So there I continue. So substituting correctly, you now have 5 times y, the 5 place, the 5 here is your du dx, then v is your y, plus u is your 5x, then dv dx is this dy dx. So there, multiplying correctly, you now have 5y plus 5x times dy dx. And this is the derivative of this 5xy using the product rule. Then I will now come back to my chain rule formula and continue. So I now have the derivative of this 5xy, which is 5y plus 5x times dy dx. So I'm just going to write it here. So this is what I'm going to have, 5y plus 5x multiplied by dy dx. So there I continue. So step 1 is now completed, that I have obtained the derivative of both sides of the equation. So what remains is to make a dy dx subject of the formula, that is solve for dy dx. So there I continue. I have a term in dy dx by the right hand side here. I have another term in dy dx by the left hand side there. So what I'm going to do, I will now try to bring all those the terms that have dy dx to the left. Those that don't have dy dx, I will move them to the right hand side of the equation. So in that case, I will now take this 5x dy dx to the left, and I will take this 3x squared to the right. So let me do that. So I'm going to have 3y squared dy dx, which I just copied here, then minus 5x dy dx, which I shifted to the left. It changes to minus, equals to my 5y, which I copied, then I shifted 3x squared to the right, which becomes negative. So I continue. Remember, we are targeting to make dy dx subject in this case. So there, I can now factorize dy by dx because it's common to these two terms. So factoring it, I will now have dy by dx, then open my bracket. Then I'm going to have 3y squared minus this 5x. Then close the bracket, equals to, you copied your right hand side. We are targeting to make dy dx subject of the formula. So in that case, I will now divide both sides by this very bracket. So dividing both sides by this bracket gives me dy by dx equals to the right hand side, which is 5y minus 3x squared divided by 3y squared minus 5x. And this is the dy by dx of this very function. And this is your implicit rule. With these few examples, I hope, my dear students, you'll be able to find a derivative of implicit function. Thank you for your attention, and let me just move to the last segment versus fun. So let us learn the relationship between numbers in the Lucas sequence and the golden ratio. Let's just try to recall what are Lucas numbers. Lucas numbers is just a number starting with 2 and 1. And other numbers are obtained by adding the last 2 to get the next term. So addition of 2 and 1 gives you this 3. Addition of 1 and 3 gives you 4. Addition of 3 and 4 gives you 7. Addition of 4 and 7 gives you 11. This is what we call the Lucas sequence. And let's find out how these numbers are having a relationship with the golden ratio. So it says that the powers of the golden ratio, that is, if this number 1.618 is raised to a particular power, and that result when rounded, the result when rounded will now be one of those numbers in the Lucas sequence. So let's do it and see. So 1.618 raised to the power of 2. If you do it correctly, it will give you 2.617924. And you can see when this number is rounded, it gives you 3, and 3 is one of the numbers in your Lucas sequence. So you can see that this number approximately to 1 SF, it will be nothing but 3. And 3 is among the numbers you have in the Lucas sequence. Let me just take another power of the golden ratio. Another power of the golden ratio is when the golden ratio is raised to the power of 3. If you do this correctly, you have 4.23580 and so on. And if this number is rounded to one significant figure, or to the nearest whole number, is nothing but 4. And 4 is among the numbers. Look at it in the Lucas sequence. Let me take another power of the golden ratio. This 1.618 raised to the power of 4. If you did it correctly with your calculator, this is what you are going to have as your result, 6.853260 and so on. And when this is rounded to one significant figure, or to the nearest whole number, you have 7. And look at the 7 is another number in your Lucas sequence. So this golden ratio is having strong relationship with the numbers in the Lucas sequence. As you can see, when you now raise those golden ratios to appropriate power and rounded the result, what you have in the end is one of the numbers in the Lucas sequence. So you can now find the other powers of the golden ratio and round them and see whether it's something among the decimal numbers that you're going to have. Thank you for your attention. We see more of these amazing things in mathematics in our subsequent